Hey guys! In this video we're going to talk about Le Chatelier's principle and how that relates to equilibrium and everything that we've been talking about in chemistry since before this video. So, what on earth is Le Chatelier's principle? So essentially, whenever you have a chemical equation, right, that is in dynamic equilibrium, meaning that it has already been stabilized, the net amount of molecules on both sides is going to be the same because the rate of the forward and reverse reaction is the same, right? So once all of that's already been stabilized, then depending on different stresses, right, or conditions that are going to happen to our reaction, we're going to see a change, okay? So just as your body likes to maintain, this happy state called homeostasis, right? We like to maintain a sense of equilibrium, meaning whenever you get really cold, you start shivering because that produces body heat, which then wants to warm you up back to your normal temperature. The same way, if we have a stress that comes in and messes up our equilibrium that we have reached in our chemical equation, we're going to see a change that wants to counteract that. So we have three different types of stresses that can affect our chemical equation. So the first thing is a change in concentration, and that can come in concentration of one of the reactants or one of the products. Another one is going to be change in pressure or volume. So this one is kind of the same, and I'll get to explain why we kind of consider it to be the same thing in a second. And then the third one is going to be a change in temperature. So let's start with a change in concentration first. So let's take a look at this equation, which you've already seen. And let's say that it's already reached its dynamic equilibrium, right? So the rate of the forward and the reverse reactions are already the same. We're good. Now, let's say that I add some nitrogen, right? Okay, all of a sudden, we have more of the reactant side than we were intending to, right? Because it's already reached equilibrium, so then if I add even more of the reactant side, then it's like, okay, all right, now we have too many reactants compared to the product, so now we have to make more products, okay? The same way that if I add more product, right, after the equation has already reached equilibrium, so if I add ammonia, it's like, uh-oh, okay, now we're all out of balance, we have too many products compared to the amount of reactants that we have. Okay, we gotta go in the reverse direction of the reaction, so right to left, and create more of the reactants. That way the equation, or rather the whole situation, is balanced. So that's whenever we have a change in concentration. If we have a change in pressure or volume, so let's take a look at this, right? If we have pressure, right, so like let's say we have a vessel, right, like almost like a piston, right? And if we were to push down on this piston, we are going to literally decrease the amount of space that these molecules have in order to float around, right? But as you decrease space, you're also forcing these molecules to run into each other more frequently. The same way that if you have a room, like if you have 100 people in the White House, that's a ton of space, right? Like you could all probably be in a different room. I don't know how many rooms the White House has, but that's not important, right? You have enough room for people to like spread out, kind of mingle, right? But if you put 100 people in your bedroom, that's going to be a lot of people in a very small space, right? So then you're going to have a lot more chance of people bumping around into each other, and then, you would just feel really claustrophobic. In the same way, we have an increase in pressure whenever we have a decrease in volume, right? Because whenever you decrease the size of the room, all those molecules are going to have to be a lot closer together, which is pressure. On the flip side, if we have an increase in volume, meaning that we make the room bigger, then you're going to have less pressure because these molecules can all spread out. So how does this relate to chemistry, right? So if we take this room that these molecules are in, right, this vessel, and let's say this has already reached its dynamic equilibrium, and then we shrink this room, right? Well, if we take a look at the reactant side, at equilibrium, there are 4 moles of molecules. 1 for the nitrogen, 3 for the hydrogen. But if we look at the product side, we only have 2 moles. So what that means is if we are going to decrease the pressure, right, or rather, let's actually start with increase. Let's say we increase the pressure and then thus make the volume of that room smaller, then our equation is going to want to do something to counteract this balance, right? So all of a sudden, we have too many molecules in a really, really small space and everything is freaking out. So what do? Do we want more moles of molecules or less? We want less because those molecules don't want to bump into each other as much. So whenever we decrease the volume, thus increase the pressure, we're going to have a shift in our chemical equation that is going to go to the side with less moles. So in that case, this is going to be our product. Let's take the opposite scenario into example. If we make the room super, super big, then there's no reason to really make sure that our equation is basically as efficient as possible and we have a less amount of stuff in the room, right? We have ultimate space. So in that case, we're actually going to have a shift, according to this equation, to the left because you can afford to have more moles in that space. So it's just trying to counteract what's already been done, right? If you have a really, let's say you've already reached equilibrium, you want to decrease the space, then, all right, we need also a less number of moles. That way they don't bump into each other as much, which is why in that case we get products. So that's how pressure and volume relate. Now let's go to the last one. Let's go to temperature. This one is a little bit more complicated, but you can do this. All right, so let's take a look at this reaction. This reaction has an increase, right, in heat on the product side, right? Meaning that this is going to carry more energy. This reaction is called endothermic because the products have a greater energy than the reactants. In that case, what that means is that we can use heat as a reactant because when all of this works together and you go this way, this product has actually absorbed this heat right here. Heat is one of the reactants of this reaction. So whenever heat is a reactant, then the equation is going to be endothermic. So then, we're going to treat heat as a reactant as we would anything else. Let's go back to concentration. If you increase the temperature of this reaction, what do you think will happen, given that heat is a reactant? You're going to make more product because you are adding more of the reactant. So then it's going to shift it to the right and increase the rate of the forward reaction. Now let's think about an exothermic reaction. Exothermic means that the reactants, right? So whenever you actually have a reactant, the reactant is going to have more energy than the product, which means that whenever you go to the right, you're going to release heat. So in that case, heat is going to be on the right side of the equation. So in that case, if you're going to increase the temperature, then it would go from right to left because, as I said earlier, heat would be on the product side, and then it would have to kind of rebalance and maintain the sense of equilibrium. All right, guys, I know this was a lot in this video, so feel free to rewatch it, but let's practice now.